Hello, treasure hunters. It's me, your host, ready to take you on another journey into the cosmos. Let's talk about something that has captivated the human imagination for centuries: time travel. We've seen it in countless movies, read about it in epic novels. The idea of stepping into a machine and witnessing the past or shaping the future. It has always been the ultimate science fiction fantasy, a concept relegated to the pages of a book or the silver screen. But what if I told you that the line between science fiction and science fact is beginning to blur? What if the universe is stranger, more wondrous, and more accommodating to our wildest dreams than we ever thought possible? Recent breakthroughs at the very edge of our understanding are challenging everything we thought we knew about the linear progression of time. We're talking about bizarre, almost ghostly particles that appear to move backward through time, defying the fundamental laws of causality as we understand them. We're delving into the spooky world of quantum physics, where reality itself seems to bend and twist in ways that could, just maybe, open a door to the past. The universe is whispering its secrets, and we are just now beginning to learn its language. So, strap in, because we're about to explore the very real scientific discoveries that could one day make time travel a reality. Before we fire up our theoretical time machine, do me a favor. If you enjoy pondering the great mysteries of the universe, hit that like button, subscribe to the channel, and ring that notification bell so you never miss an expedition into the unknown. And I have a question for you. If you could travel through time just once, where or when would you go? Would you witness the dinosaurs, meet a historical figure, or perhaps peek into your own future? Let me know your ultimate time travel destination in the comments below. I can't wait to read your ideas. Now let's begin. Our journey begins not with a giant flashy machine, but in the realm of the infinitesimally small. To understand the profound possibilities we're discussing today, we must first confront a fundamental concept: the arrow of time. Think about it. An egg falls and shatters on the floor. You can't unshatter it. A drop of ink disperses in a glass of water. You can't undisperse it. This is entropy, the universe's unwavering tendency towards disorder. This forward march from order to chaos is what gives us our sense of past, present, and future. It's a one-way street, or so we thought. Scientists, in their tireless quest to understand the building blocks of reality, have stumbled upon some truly perplexing characters in the cosmic play. These characters are subatomic particles, the tiny constituents of everything you see around you, and some of them don't seem to play by the rules. Take, for instance, the neutrino. These are incredibly light, elusive particles, often called ghost particles because they pass through most matter as if it weren't even there. Billions of them are streaming through your body right now, completely unnoticed. In certain highly complex experiments, like those conducted in massive underground detectors, physicists have observed behaviors that are, to put it mildly, weird. Some interpretations of the data suggest that certain types of neutrinos might be their own antiparticles. This concept, known as being a Majorana fermion, has staggering implications for our understanding of time. Why is this so significant? Let's turn to the work of the great physicist Richard Feynman. He proposed a fascinating idea, that an antiparticle is simply a regular particle moving backward in time. Imagine a particle's journey as a line on a graph of spacetime. If the line is moving forward in the time dimension, you see a particle. But if that line were to loop around and start moving backward in the time dimension, you would perceive it as an antiparticle. It's the same particle, just on a different leg of its temporal journey. It's a mind-bending concept that treats time as just another dimension, one that can be traversed in more than one direction, at least on this quantum level. So, when experiments hint that a neutrino might be its own antiparticle, they are inadvertently suggesting that this particle could, in a mathematical sense, be its own temporal reflection. It's like looking in a mirror and seeing your past self looking back. This doesn't mean we can build a neutrino-powered DeLorean just yet. The effect is statistical, theoretical, and buried deep within complex quantum field theory, but it cracks the door open, ever so slightly. It introduces a fundamental symmetry where the distinction between moving forward and backward in time becomes ambiguous. It's the universe showing us that the rules we take for granted on our macroscopic scale might be more like friendly suggestions in the quantum realm. Think of it this way: the universe, at its most fundamental level, might not have a preferred direction for time. The arrow of time that we experience, our aging, our memories of the past but not the future, could be an emergent property, something that appears only on a large scale, like the wetness of water emerging from the properties of individual H2O molecules. The individual molecules aren't wet, but put enough of them together, and the property emerges. Perhaps time itself is like that. The underlying physics might be perfectly symmetrical with respect to time's direction. This idea is supported by looking at the fundamental equations of physics, like those of general relativity or quantum mechanics. For the most part, the math works just as well if you plug in a positive value for time or a negative one. The equations don't inherently forbid backward time travel. It's the consequences, like the shattering of causality, the principle that a cause must precede its effect, that make physicists deeply uncomfortable. The famous grandfather paradox is a direct result of this discomfort. If you could go back and prevent your grandparents from meeting, how could you have been born to go back in the first place? Yet the universe keeps showing us these little hints, these tantalizing clues. The observation of particles that seem to behave like their own time-reverse twins is one of the most powerful. It tells us that the rigid, one-way flow of time we experience in our daily lives is not the whole story. It's a crucial piece of evidence that suggests the fabric of spacetime might be more pliable, more exotic, and more open to manipulation than our intuition allows us to believe. The one-way street of time might in fact have hidden U-turns. These discoveries force us to ask profound questions. Is time fundamental, or is it an illusion? If particles can travel backward in time, what does that mean for the information they carry? Could we, theoretically, receive a message from the future, encoded in a beam of neutrinos? The technical hurdles are of course monumental, perhaps even insurmountable. We're talking about detecting and interpreting the behavior of single, ghostly particles in a sea of cosmic noise. But the theoretical possibility is what's so electrifying. It changes the conversation from impossible to how. The scientific community remains divided as it should be. Extraordinary claims require extraordinary evidence. Many physicists believe these are just mathematical quirks, useful ways of modeling particle behavior that don't correspond to any physical reality of time reversal. They argue that causality is an unbreakable law, and any theory that violates it must be incomplete or wrong. But others maintain a more open mind, suggesting that our understanding of causality itself might be flawed or incomplete. What we are witnessing is science in action. It's the slow, painstaking process of chipping away at ignorance, of following the data wherever it leads, even if it leads to conclusions that sound like pure science fiction. The strange behavior of these elementary particles provides the first tentative checkmark on our list of is time travel possible? It's not a definitive yes, but it's a very loud and intriguing maybe. And in science, maybe is the most exciting word there is. Now, let's venture deeper into the bizarre landscape of the quantum world, to a phenomenon that Albert Einstein himself famously called spooky action at a distance. He was talking about quantum entanglement, and its implications are so strange, so counterintuitive, that they continue to baffle and inspire physicists to this day. And, you guessed it, they might just hold another key to tampering with time itself. So what is entanglement? Imagine you have two coins that are magically linked. You give one to a friend and keep one for yourself. Your friend travels to the other side of the galaxy. The moment you flip your coin and it lands on heads, you know instantly that your friend's coin has landed on tails. This is the essence of entanglement, but with subatomic particles instead of coins. When two particles, like photons or electrons, are created in a certain way, they can become entangled. Their properties, such as their spin or polarization, become linked in a profound way. No matter how far apart you separate them, across a laboratory or across the universe, measuring the property of one particle instantaneously influences the property of the other. There's no signal sent, no travel time, the connection is immediate. This apparent violation of the cosmic speed limit, the speed of light, is what made Einstein so uneasy, but experiment after experiment has proven it to be a real feature of our universe. So how does this spooky action connect to time? The link is subtle but profound. It challenges our classical notions of space and time or locality, the idea that an object can only be influenced by its immediate surroundings. Entanglement shows us a form of non-locality, a connection that transcends spatial distance. Some physicists theorize that if entanglement can transcend space, perhaps it can also transcend time. This line of thinking has led to some fascinating, albeit highly speculative, concepts like temporal entanglement or entanglement in time. The idea is this. What if particles could be entangled not just across space, but across time? Imagine creating an entangled pair of photons. You measure the first photon right now in the present. But what if its entangled partner isn't measured until some point in the future? The theory of temporal entanglement suggests that the measurement you make now could be correlated with the result of the measurement made later. It's as if the universe knows what the future measurement will be, or perhaps the two events separated by time are still somehow one single unified quantum event. Let's unpack that a little more because it's a real mind-bender. In a famous thought experiment, physicist John Wheeler proposed a delayed choice experiment. In it, the decision to measure a particle's property is made after the particle has already passed the point where that property should have been determined. The results suggest that the future measurement affects the particle's past reality. Real-world versions of this experiment have been carried out and they confirm Wheeler's strange predictions. The universe, it seems, does not decide a particle's history until it is measured. The act of observation in the future reaches back and defines what happened in the past. This doesn't give us a direct path to visiting the Roman Empire, but it fundamentally alters our perception of causality and the flow of time. If a choice made in the future can influence an event in the past, then the rigid one-way street of time suddenly looks more like a complex network of interconnected pathways. The past might not be as set in stone as we believe. It suggests that the relationship between cause and effect might be a two-way conversation, not a one-way monologue from past to future. Consider the implications for information. The instantaneous connection of entanglement across space, while real, cannot be used to send information faster than light. The outcomes are correlated, but they are also random. You can't force your particle to be spin up to send a 1 to your friend, but with temporal entanglement, the game might be different. Could we devise an experiment where a choice made today influences a measurable outcome of a particle from yesterday? If so, we could, in principle, send a single bit of information one day into the past. It would be the most profound discovery in human history. Of course, the universe has a way of protecting its paradoxes. The no-communication theorem is a principle in quantum mechanics that prevents faster-than-light signaling using entanglement, and most physicists believe a similar principle would prevent sending information backward in time. Any attempt to exploit these quantum quirks to create a paradox would likely be smoothed over by the inherent randomness and uncertainty of the quantum world. The universe seems to play its cards very close to its chest, ensuring that causality, on a macroscopic level, is preserved. However, these experiments are pushing the boundaries of what we thought was possible. They are forcing us to reconsider the nature of time itself. Is time an absolute flowing river, as Newton imagined, or is it part of a more complex, interwoven tapestry of spacetime, as Einstein proposed? Quantum mechanics adds another layer of weirdness, suggesting that this tapestry might be stitched together with non-local threads that connect distant points in space and, just maybe, in time. The mystery of entanglement serves as a powerful reminder that our everyday intuition is a poor guide to the fundamental workings of reality. The universe operates on a set of rules that are far stranger and more beautiful than we can easily comprehend. While spooky action at a distance may not be a blueprint for a time machine, it demonstrates that the connections within our universe are deeper and more mysterious than we know. It shows that past, present, and future might not be as distinct as they appear, but rather different aspects of a single, vast, and interconnected quantum reality. Let's shift gears from the quantum realm of the very small to the cosmic scale of the very large. Our next potential method for time travel comes straight from the pages of Albert Einstein's own masterpiece, the theory of general relativity. This theory describes gravity not as a force but as a curvature of a four-dimensional fabric called spacetime. Massive objects like stars and planets create dips and curves in this fabric, and that curvature is what we experience as gravity. But what if you could curve spacetime so much that you could poke a hole right through it? This is the tantalizing concept of a wormhole. Imagine spacetime as a giant sheet of paper. To get from one point on the paper to another, you have to travel across the surface. But what if you could bend the paper over, connecting the 2 points directly, and then punch a pencil through both layers? That shortcut, that tunnel through a higher dimension, is a wormhole, or as it's more formally known, an Einstein-Rosen bridge. In theory, it could connect two vastly distant points in space, allowing you to traverse millions of light years in the blink of an eye. It would be the ultimate cosmic shortcut. But how does a shortcut in space become a gateway through time? This is where things get even more interesting, and it involves combining the ideas of relativity. According to Einstein's theory of special relativity, time is relative. The faster you move through space, the slower you experience time compared to a stationary observer. This phenomenon, known as time dilation, is not theoretical, it's a proven fact. GPS satellites have to account for it to remain accurate as their clocks tick slightly faster in orbit than ours do on the ground. Now let's apply this principle to our wormhole. Imagine you have a wormhole with two mouths, let's call them mouth A and mouth B. They are initially right next to each other and their clocks are synchronized. Now, you take mouth B on a journey. You accelerate it to near the speed of light, fly it around the galaxy for a while, and then bring it back to rest near mouth A. Due to time dilation, the clock at mouth B will have experienced less time than the clock at mouth A. Let's say mouth A's clock now reads the year 2050, while mouth B's clock only reads 2030. You have now created a time machine. If you enter mouth B in the year 2030, you will travel through the wormhole and exit from mouth A in the year 2050. You've just jumped 20 years into the future. But it gets better. What if someone in the year 2050 enters mouth A? They would travel through the wormhole and exit from mouth B in the year 2030. They have just traveled 20 years into the past. You haven't just built a shortcut through space, you've built a bridge through time. The wormhole connects two different points in space-time. This sounds incredible, and it is entirely consistent with the mathematics of general relativity. However, before you start drawing up blueprints, there are a few rather significant cosmic catches. The first major problem is stability. The kind of wormhole described by Einstein and Rosen is incredibly unstable. It would form and then pinch off so quickly that not even a single photon of light would have time to pass through it. To keep a wormhole open long enough for something to traverse it, you would need something very special. You would need a form of matter with properties unlike anything we've ever seen. You'd need exotic matter. This isn't just matter that's rare or unusual. It's matter that has negative mass, or more precisely, negative energy density. Think of it this way. Normal matter with positive mass curves space-time, creating the gravity that pulls things together. This exotic matter would need to have the opposite effect. It would need to possess a kind of anti-gravity, pushing space-time apart to prop open the throat of the wormhole and prevent it from collapsing. The problem is, we have never observed any exotic matter in the universe. While some quantum effects like the Casimir effect can produce localized regions of negative energy density, they are incredibly small and fleeting. No one knows if it's possible to gather enough of this stuff to stabilize a macroscopic wormhole. It might be that the laws of physics themselves, through principles like quantum interest, forbid the existence of stable, traversable wormholes on a large scale, precisely to prevent paradoxes from occurring. The second, equally daunting challenge is actually creating a wormhole in the first place. General relativity tells us they are possible, but it doesn't tell us how to make one. They might form naturally in the incredibly turbulent high-energy conditions of the early universe or at the heart of a black hole, but we have no evidence for this. Creating one from scratch would likely require manipulating space-time on a level that would demand energies comparable to the output of an entire star, or perhaps even a galaxy. We're talking about a level of technology so far beyond our own that it might as well be magic. So, while the wormhole remains the most theoretically sound model for a true time machine based on classical physics, it comes with a hefty instruction manual filled with impossible ingredients and Herculean tasks. It's a beautiful theoretical construct, a testament to the power of Einstein's vision. It shows us that within the known laws of physics, time travel isn't explicitly forbidden. But the universe seems to have placed some very large, perhaps insurmountable, practical barriers in the way. The cosmic tunnels may exist in the equations, but finding or building one remains firmly in the realm of far future science fiction. Our exploration now takes us to one of the most recent and mind-boggling discoveries in physics, a completely new phase of matter. We're all familiar with the standard phases: solid, liquid, gas, and plasma. These are defined by the spatial arrangement of their atoms. In a solid crystal, like a diamond or a snowflake, atoms are arranged in a repeating pattern in space. This spatial order is what gives them their structure. But in 2012, Nobel laureate Frank Wilczek asked a revolutionary question: could a structure repeat in time as well? This question gave birth to the concept of the time crystal. A time crystal is a phase of matter whose constituent parts move in a periodic, repeating pattern, even in its lowest energy state, or ground state. This is the truly weird part. Normally, in a ground state, things should be still. A regular crystal in its lowest energy state is just a static, ordered lattice of atoms. There's no inherent motion. But a time crystal is different. Even at its absolute minimum energy, it has a built-in tick. Its atoms flip or oscillate back and forth at a regular interval, all without any energy being put into the system. It's like a clock that runs forever without ever needing to be wound. For several years, time crystals were purely theoretical. Many physicists argued they were impossible, that they would violate the laws of thermodynamics. A system that moves forever without energy input sounds suspiciously like a perpetual motion machine, a concept long debunked. But the key distinction is that you can't extract useful work or energy from a time crystal. Its motion is locked in its ground state. It's not creating energy from nothing, it's simply manifesting a new and bizarre form of temporal order. Then in 2016 the impossible happened. Two independent teams of scientists, one at the University of Maryland and another at Harvard, announced that they had successfully created time crystals in their labs. They didn't forge them from some exotic new element. They built them using systems of trapped ions and impurities in diamonds. By zapping these quantum systems with precisely timed laser pulses, they were able to coax them into a state where they would oscillate at a frequency that was a fraction of the driving pulse. The system had taken on a temporal rhythm of its own, just as Wilczek had predicted. Imagine you're pushing a child on a swing. You push once, every 2 seconds. But the swing only reaches its highest point every 4 seconds. The swing is oscillating at half the frequency of your push. This is analogous to how these first-time crystals work. They were driven systems, but their response showed a new emergent temporal pattern that was not present in the initial push. The crystal had developed its own internal clock, its own repeating beat in time. So, what does this have to do with time travel? On the surface, not much. A time crystal won't transport you to the Jurassic period, but its existence is profoundly important, because it fundamentally changes our understanding of time itself. It shows that temporal order is a real physical property that matter can possess, just like the spatial order of a regular crystal. It suggests that time is not just a passive background coordinate, but an active player in the structure of reality. The existence of time crystals proves that systems can spontaneously break time translation symmetry. This is a fancy way of saying that the laws of physics are the same today as they were yesterday, and will be tomorrow. A time crystal violates this principle on a microscopic level because its state is different from one moment to the next, in a repeating pattern. It has a preferred tick in time. This was a symmetry that many physicists thought was absolute and unbreakable. Finding a system that breaks it is a monumental discovery. This could have far-reaching implications for technology. The incredible stability of a time crystal's oscillation could lead to the development of ultra-precise clocks for quantum computers, or incredibly sensitive sensors for detecting minute changes in gravitational or magnetic fields. A quantum computer built with time crystal-like components might be far more robust and resistant to the errors that currently plague these delicate machines. But on a more philosophical level, time crystals force us to ask deeper questions. If matter can have a structure in time, what other temporal properties might be possible? Could we manipulate this temporal order? Could we create materials with more complex temporal structures, not just a simple tick-tock, but a pre-programmed sequence of states? Could we, in essence, program a material's evolution through time? This is highly speculative, but the discovery of time crystals opens up a whole new field of temporal materials science. Time crystals are a brand new frontier. We are just beginning to scratch the surface of what they are and what they can do. They are a stark reminder that the universe is constantly revealing new layers of complexity. They might not be a vehicle for time travel, but they are a form of it. They are matter that lives and breathes in the fourth dimension, possessing a structure that repeats not just in space, but through time. They are a ticking clock at the heart of matter, a whisper from the universe that our understanding of time is far from complete. Our final chapter brings us to the cutting edge of experimental physics, where scientists are not just theorizing about time, but actively trying to manipulate its direction in the laboratory. We've discussed the arrow of time, the principle of entropy that dictates why things break but don't unbreak. This arrow seems like an absolute law of the universe. But what if it's more of a statistical probability? What if, On a small enough scale, you could cheat entropy and make time appear to run backward. This is precisely what a team of physicists from Russia and the US managed to do in a groundbreaking experiment. Using a basic quantum computer, the scientists set up an experiment that was the quantum equivalent of a game of pool. At the beginning, the billiard balls, in this case the quantum states of qubits, were arranged neatly in a corner, an ordered, low-entropy state. Then, they let the system evolve naturally. Just like a real break shot in pool, the qubits quickly spread out into a chaotic, disordered, high-entropy state. This is the normal, forward arrow of time in action. Order descends into chaos. But then came the revolutionary part. The researchers used a special, carefully constructed algorithm to manipulate the quantum computer. This program essentially reversed the evolution of the system. It was like giving every single particle a perfectly calculated kick in just the right direction. To their astonishment, the chaotic, disordered system began to reverse itself. The scattered qubits started to move back towards their initial positions, and a moment later, they were once again arranged neatly in the corner, back in their original, low-entropy state. For a brief moment within this quantum system, time had effectively run backward. It's crucial to understand what this does and doesn't mean. This experiment did not violate the second law of thermodynamics. The universe as a whole still became more disordered. A great deal of energy and information was required to run the quantum computer and the special algorithm that reversed the system. The magic was all in the external manipulation. It's like filming a pool break and then playing the video in reverse. The balls on the screen will magically reform into a triangle, but the camera, the screen, and the person watching are all still moving forward in time and consuming energy. However, the experiment is still profoundly significant. It demonstrated that on a quantum level, the arrow of time is not an absolute prohibition, it's more of a strong suggestion. It showed that if you have perfect control over a quantum system, you can, in principle, reverse its temporal evolution. The scientists calculated that for even a simple system like a breaking rack of billiard balls in the real world, the probability of it spontaneously reversing itself is practically zero. You would have to wait longer than the age of the universe to see it happen. But in the controlled environment of a quantum computer, they made it happen on demand. This opens up a fascinating philosophical and practical debate. If the arrow of time is simply a matter of statistics and probability, then time reversal is not impossible, just mind-bogglingly improbable. What these experiments do is give us a way to stack the deck, to manipulate those probabilities. The goal of these researchers isn't to build a time machine to send people back to the past, but to improve the performance of quantum computers. Reversing the evolution of a quantum state could be a powerful way to correct errors and undo mistakes in a quantum calculation. These experiments are part of a broader field of research exploring the fundamental nature of time and causality. Other experiments have explored retrocausality, the idea that influences can travel backward in time to affect past events. While still controversial, some interpretations of these experiments suggest that what happens in the future can subtly influence what happens in the past, echoing the delayed choice experiments we discussed earlier. It's as if the universe has a slight blur in its temporal focus. What all these experiments, from time-reversed quantum states to delayed choice measurements, have in common is that they are chipping away at our classical intuitive view of time. They show us a universe where time is not a simple monolithic river flowing in one direction. Instead, it's a complex, dynamic, and malleable feature of reality, especially at the quantum level. The past, present, and future may not be as cleanly separated as we like to think. This doesn't mean you should expect a visit from your future self tomorrow. The gap between reversing the state of a few qubits in a computer and reversing the state of a macroscopic object like a person is unimaginably vast. The amount of information and control required would be beyond astronomical. Any interaction with the outside environment would destroy the delicate quantum coherence needed for such a reversal. But that doesn't diminish the achievement. These experiments are a proof of concept. They are like the first, tentative flights of the Wright brothers. They didn't cross the Atlantic, but they proved that controlled flight was possible. Similarly, these physicists have proven that, under the right conditions, the arrow of time can be bent. They have taken an idea that was once pure philosophy and brought it into the realm of experimental science. They are learning to play the cosmic game of pool not just forward, but in reverse. So, where does this leave us? We've journeyed from ghostly particles and spooky entanglement to cosmic tunnels and ticking crystals. The evidence suggests that the rigid one-way flow of time we experience is not the full picture. The universe, at its most fundamental level, seems to have back doors, hidden pathways, and a much more fluid relationship with time than we ever imagined. While a practical time machine remains far beyond our grasp, the question has shifted from if to how. The pursuit of these answers will continue to drive science and technology in incredible new directions. The journey into the nature of time is a journey into the heart of reality itself. If you enjoyed this deep dive into the mysteries of the cosmos, don't let the exploration end here. For more thought-provoking conversations, be sure to check out the Brightside podcast available on Spotify. We cover everything from science and technology to the biggest questions about life and the universe. If you listen and enjoy it, please consider leaving us a positive review. It really helps us out. And for an endless stream of fascinating videos and articles just like this one, head over to the Brightside website. There's always something new to discover. Finally, a quick but important reminder, this video is created for educational and entertainment purposes. The theories and experiments we discussed are at the very edge of human knowledge, and are subject to ongoing research and debate. It's a fascinating look at what might be possible, but always remember to approach such topics with a healthy dose of critical thinking and scientific curiosity. Thank you for joining me on this incredible journey through space and time. Stay curious, and I'll see you in the next video, or maybe in the last one.